Okay, welcome to this, one of the final sessions of our conference. I'm Steve Austin. I'll be talking to you about the flood, post-flood boundary. That's my topic this morning, and Kurt's going to follow and talk about the post-flood as well. But I want to talk about the boundary, okay, thinking about the boundary. And Kurt's going to probably talk, I don't know what Kurt's going to talk about, but I'm sure he's going to talk about what life was like in the interval between Noah getting out of the ark and the present, okay? And so, but I'd like to talk to you about understanding that boundary between the flood and the post-flood. Let me say there's an incorrect emphasis, okay, and talk to you about the incorrect emphasis. What you want to see, or maybe you want to see, is a chart of the geologic column, okay, and all the stacked up systems or ages of the geologic column, and then you want me to have an arrow pointing at what? The flood, post-flood boundary in the geologic column. That is a bad emphasis, okay? Why? Because the geologic column is an abstraction, and assigning things a position in an abstraction, which is supposed to approximate reality, may be a real bad thing to do. Instead, I'd like to change the emphasis. I'm looking for the footprint of Noah stepping off the ark. And that footprint is the flood sediment underneath. Okay, and what sits on top of it, all the sand grains and mud that fell on top of that, that is the post-flood. Okay, the footprint of Noah is the golden spike, if you will, that defines the flood, post-flood boundary. And if I think that way about looking at that, then I can tie the other things in that are rather abstract, formation boundaries, where I am relative to where Noah landed, that kind of thing, and I can make the assignment better. Anyway, so think the way I'm thinking. Think about that golden spike, and think about what that was like. Think about the processes that were going on in the flood and the post-flood, and relative to that golden spike or that position, and you'll do well at getting this controversial subject. Okay, and it is a controversial subject among creationists, and man, I get some people riled up real big time just by talking the way I talk, and that needs to be neutralized, and so we need to, instead of pointing at an abstraction, let's talk about real strata. The real strata, of course, is what Noah walked on. Okay, the post-flood flood boundary, I'm going to give you 7 boundary criteria that I think about, and then if you think the same way I'm thinking, maybe we'll come to some kind of agreement. If you don't, maybe it'll become controversial. But I'm thinking about what? I'm thinking about geologic processes and how they change through time, and I might be able to use these characteristics or criteria to evaluate that idea of the flood, post-flood boundary. First is horizontal tectonics gives way to vertical tectonics. I think you can understand from my previous lecture the way I'm thinking about this. Horizontal tectonics, continental sprint, if you will, was in my way of thinking, the primary deformational process associated with the global flood. And horizontal tectonics, plates crashing into each other, plates pulling apart, plates sliding by each other, that's the general nature of the tectonics of the flood. Of course, it continues into the post-flood, but the style of tectonics changes more to vertical. So I'm looking for the change from horizontal tectonics giving way to vertical tectonics. And vertical tectonics, in other words, uplift and down warp, is the the signal, if you will, that I need to think about first. I would say that's the first thing I need to think about. The second thing I need to think about are beveled erosion surfaces, which would be the retreat of the flood. They would mark the retreat of the flood because the flood waters are not channelized, they're broad, and the retreat of flood waters lasted 7 months. Okay, 7 months for waters to retreat off the earth, and those beveled, widespread regional erosion surfaces will be cross-cut by channelized erosion in the post-flood period. Are you with me on that? You're thinking the way I'm thinking? So I need to think about tectonics and erosion beveled surfaces. So I'm looking for something that rather obvious, a beveled surface, and then I'm looking for the cross-cutting of that beveled surface by the post-flood process, by channelized erosion. Okay, and the channels are the style of hydraulic erosion that's prevalent today. Sheet erosion is not with us very much today, and so that's another criteria, boundary criteria. Then I've got four sedimentary evidences, or largely sedimentary evidences, and one paleontologic evidence or criteria. Okay, let's take a look at these four sedimentary criteria. Sedimentary deposits confined within structural basins. Okay, in the flood, sedimentary deposits are regional, interregional, very broad, and in the post-flood, sedimentary deposits are going to become basinal, okay, and they're going to be confined to basins. And so, especially if vertical tectonics, uplift and down warping is occurring, we're going to isolate or strand particles that are moving around into basins. Mass wasting is going to be occurring. You know, the earth is like a plate of mashed potatoes, beveled surfaces, now it's going to be channeled, and erosion is going to be in structural basins. So think that way, and that'll help you understand the flood, post-flood boundary, I would say. A fourth thing you want to think about is the shapes of deposits adjacent to elevated areas. Wedge-shaped deposits. You're going to look for big, thick wedges that start thin and then become extremely thick, okay? And that would be marginal to what? A fault or to an uplifted terrain, say, okay? And those wedge-shaped deposits are going to be in down-sunk troughs. Okay, you can think of, what I think of wedge-shaped deposits, I think immediately of a delta, right? A delta is a sedimentary deposit in the boundary between two adjacent regions, wedge-shaped deposits. And then number 5 is sediments derived from local sources. I'm thinking that because regional sedimentary process is largely an interregional and global sediment transport is shutting down, that I'm going to see in the post-flood strata those sources be local. And especially if sedimentation is basinal, then around the basins can be the sources of the sediment. So I'm looking for rock types and particle types that are from local sources. Are you with me on that? I think sediments derived from local sources. And so I'll tell you some things that I look for as a petrologist. I'm looking for heavy minerals in the sedimentary rocks that look like the heavy minerals in the associated granites around a basin, say, something like that. So sediments derived from local sources, and so I can appreciate that. It's generally understood that the heavy minerals in the Coconino sandstone came from extremely far away in the Grand Canyon. There is a broad layer covering 500,000 square miles in the Rocky Mountain region and the Cordilleran in western United States. The Coconino sandstone came from somewhere, not underneath, but somewhere really distant. And so that is, that's a problem, just figuring out where things came from. People say that some of the zircons and the heavy minerals in the coconino sandstone came from the Appalachians or Grenville, orogenic belt even in Canada. Anyway, sediments derived from local sources. Coconino sandstone isn't derived from a local source. That's a flood deposit. But in the Anza Borrego Desert in California, where you have a series of fault troughs, I can see the heavy minerals in the sandstones matching the characteristic of the heavy minerals in the surrounding tonalite or granite deposit, granite formations. Okay, and then number 6 is kind of a fun one. Evidences of emergence, especially in volcanic deposits. Evidences of emergence. Now think about this one. When you have lava flooding a surface and big widespread lava flows, such as we have in the stratigraphic record, if you look at those lavas, you can see if those lava flowed in water. There's a characteristic called pillow lavas that is diagnostic of magma coming to the surface as lava being deposited underwater, and pillow lavas on Hawaii. There's a seawater reaction called palagonite. The palagonite is a kind of a greenish yellow alteration product associated with volcanics, especially basaltic rocks, and those alteration products are kind of distinctive, especially of salt water, and so that kind of thing. And so lavas expelled underwater and in seawater are going to show the characteristics, but lavas that are expelled onto a broad flat surface, they're going to show you extensive flow. They're going to have scoriaceous upper surface, like bubbles venting to the surface and things like that. Those are characteristics of emergence. Another fun one is welded tuff. You know what a welded tuff is? Welded tuff is a volcanic slurry flow deposit from pyroclastic flow. When pyroclastic flows occur, they're often extremely hot, and some of them are so big and hot that when the fragments, the volcanic fragments, are deposited, they weld together or fuse. Okay, and it's called welded tuff. You look for pumice fragments in a volcanic ash deposit that are squeezed by depositional deposition and heated by the characteristic of the pyroclastic flow. So when you have pyroclastic flows that land on a surface and it's hot and not submerged, you're going to see welded tuff. And the fusion of the pumice fragments and the volcanic ash fragments is going to show you that there was no water there. Okay, so evidence of emergence, that kind of thing. Volcanoclastic deposits that are not sorted by water are going to show you that. Like water would, if volcanoclastics are expelled in water, that's going to show you, you're going to see the separation of floating pumice clasts from sinkable larger fragments and heavier fragments. So those are some things to think about. Other evidences of emergence might be soil features like paleosols. We might see footprint surfaces, other things. You can imagine. Anyway, that's the subject that's fun to look for. And then finally, a paleontologic criteria: complete fossil ecosystems with modern flora and fauna. Okay, you understand what that's that affirmation or criteria involves. I'm looking for, in the post-flood, pretty much business as usual, sedimentary deposits with fossils that completely or largely represent an ecosystem. A lake, for example, a lake community, or a shoreline, or something like that. You can, and that's the primary evidence of a community of organisms living together. Now, think about the geologic record of the flood. What do you see? You see incomplete ecosystems. For example, the wall at Dinosaur National Monument, there's 1,500 bones on the wall at Dinosaur National Monument, but what? You don't see the trees or the wood that they ate. Okay, what did they eat? Oh, there's lots of clam fossils there. Did they eat clams? No. In fact, there are more clams on the wall at Dinosaur National Monument than there are dinosaur bones. And so that fossil display at Dinosaur National Park is an incomplete ecosystem. You see what I'm imagining? Okay, and I've studied a nautiloid bed in the Grand Canyon. Well, I see nautiloids on one horizon in a layer, and 1 billion nautiloids, say, out there in Grand Canyon and into Basin and Range region. Those represent what? A current sorted community. There's something, there's things left out or things added or put together. So that's those are my boundary criteria. Now let me take you to apply some of the boundary criteria, and then we'll just close this thinking. Okay, vertical tectonics and vertical isostasy is associated with the conclusion of the flood. There are great plates of ocean floor that were shoved underneath the margin of North America. And the relaxation and the largely the conclusion of horizontal tectonics collision with ocean floor plates has largely changed, and so we have the shutdown of subduction, essentially. And when you shut down subduction, you've got all kinds of things happening, but mainly vertical. When things are horizontal in collision, and then they change to what? Isostasy. The density needs to be compensated for. Large masses of plate under thrust below Western North America might be, the underplating idea might be the cause for uplift, because low density material shoved under the continent. And all these things, unloading and loading of the continental mass, and that creates all kinds of vertical tectonics. So look for vertical tectonics and think about it. Now you probably know where I like to look for vertical tectonics. Southwestern United States, right here. And here's my seafloor map showing the nature of the flood and into the post-flood. Now, what happened during the global tectonics associated with the flood, I believe, is horizontal convergence of the Pacific plate and the Farallon plate or Rivera plate against North America. There's actually a precursor plate that was crashing against North America, and a piece of it's down here. But anyway, the convergence of Pacific plate and the Pacific Ocean floor against Western North America, I believe, created the immediate environment where the flood occurred, and in southwestern United States and in Mexico. Anyway, this changed, okay? Head-on collision changed to a right slip type of fault situation in California. Now we have the San Andreas Fault, whereas before we had subduction underneath the continental Southern California borderland. So California borderland was under thrust, large masses collapsed, and then the motion changed, and almost a 90-degree turn. The slowing of the plate motion and the direction of the plate motion changed. And so now we're shearing the western part of North America here in California. And that's what this diagram shows. But, okay, the sheared zone here, and then you have in back of it what's called the basin and range, and then and that's where pull apart has occurred, and vertical and tectonics is dominated, but you have horizontal pull apart, and then there's the Colorado Plateau here. And the Colorado Plateau is 250,000 square miles. It wasn't pulled apart, it just basically uplifted. And what caused that uplift? Maybe underplating of sedimentary material underneath Western North America, but it didn't pull apart, it behaved as a unit and it rose tectonically and continues to rise. But anyway, the Colorado Plateau is here and it's what? 1.5 miles above sea level. And so, boy, is that vertical tectonics. And so plateaus like this are tectonically distinct. On the other side of Colorado Plateau, we have the Rocky Mountain Belt. The Rocky Mountain Belt is more vertical tectonics, even more extreme than the uplift of the Colorado Plateau is the uplift in the Rocky Mountain area. And then on the other side of the Rocky Mountains, what do we have? We have Denver Basin and the beginning of the Great Plains. And the Great Plains can be looked at as a structural province going from the Rocky Mountain front all the way across the Mississippi into Tennessee and into Illinois and into Kentucky. So this whole basin and the Great Plains is this structural province. So let's take a look at a few of those things. Okay, my favorite explanation or look, hey, take a look at this. Look at the Grand Canyon. Now, most people look at the Grand Canyon from standing on the rim, but I got a photo from the air over south rim of Grand Canyon. You're looking out over the plateau land of the Colorado Plateau, and what do you see? You see that beveled surface. What caused that beveled surface? I'm looking for a beveled surface that's incised by channelized erosion. Isn't that what I told you? What do you see? You see a beveled surface with sheet flood beveling, okay, and then you see channelized erosion. No brainer, isn't it? Okay, I think I see the flood post-flood boundary there, and the channelized erosion has got to be the post-flood, okay, and so you're thinking about that like I am. Okay. On the eastern edge of the Kaibab upwarp in Grand Canyon, we have this gigantic flexure where strata go vertical. Flood strata have been buckled up into vertical orientation. When did that happen? That's called the laramide orogeny. People call it that. But in supposedly in Cretaceous to Eocene time, that's when the plateau was flexed and uplifted. And so you're looking for the tectonics now of the uplift. Okay, good. And again, here's the tectonics. You're looking off, you're seeing the plateau tectonically. And then here is the erosion, channelized erosion. Okay, the plateau, beveled plateau surface, uplifted plateau, that could be late flood or post flood, supposedly laramide, and then of course the channelized erosion through it. You probably heard my explanation. Here it is: continental sprint caused the uplift of the plateau ultimately, and then we have the Kaibab upwarp. The whole Colorado Plateau becomes a saucer-shaped bowl. Okay. When uplift and tectonics occurs, it doesn't have to make a river system. You know what I mean? There doesn't need to be a river. It just uplifted. Okay, and so it's a basin or a saucer-shaped bowl elevated above sea level. So the edge of the bowl needs to be breached, and that's overtopping. And so that's the way I think there was water trapped on the top surface of that sheet-flooded plateau where it had sheet flood erosion initially, and then it became bowl-shaped because of the upwarp on both sides of the Colorado Plateau, and then it filled with water and lakes. I call them post-flood lakes, and there's evidence of Hopi Lake in the Bitahoche Formation out in northeastern Arizona. There are flamenco and chub fossils in the sedimentary deposits, lots of volcanic tuff, volcanic formations that indicate it was deposited in a lake, not in the ocean. So Bitahoche Formation is associated with, there's direct evidence of lake deposits. So it's a smoking gun at a scene of a crime. Duh, you know, we need to just go along with what we see. And so evidence of ponding on the surface of the Colorado Plateau obviously argues for overtopping and some type of overtopping or draining. Now that's what I imagine. Catastrophic drainage of lakes gave rise to the channelized erosion in the Grand Canyon in what? The post-flood period. Okay, here's southeastern Washington State. We have what's called the Columbia Plateau, Columbia River Plateau. Do you see the plateau surface over there? And then what do you see? The channelized erosion. So we have channelized erosion. This is Palouse River. And how was this channelized erosion done? It was done by catastrophic drainage of a lake in Montana. Lake Missoula, 500 cubic miles of water in Montana, breached an ice dam in Utah, and it came spilling over Spokane, Washington, down into the channel's Scablands area on the surface of the Columbia River Plateau and cut this canyon, probably in weeks, you know, not millions of years, but weeks. And so here's a post-flood channelized erosion canyon associated with catastrophic drainage of lakes. So that's kind of fun to think about. And for scale, you see the people over there. That's almost 400 feet deep, several hundred feet wide. And that's the Columbia River basalt, one of the hardest rocks around. And the Columbia River basalt shows individual thin flows, widespread thin flows with scoriaceous upper surfaces. That has a characteristic of being a post-flood lava lake on the surface of the Columbia River Plateau. So yeah, we can think post-flood about the lavas on the plateau, and so that's consistent with my view of the post-flood boundary. You know, one of the best places to go see the post-flood boundary or to think about it is Palo Duro Canyon, Texas. Have you been out to Palo Duro Canyon there south of Amarillo? What a marvelous thing. Because what you see at Palo Duro Canyon is what is under the whole Great Plains. Okay, it's representative of the Great Plains, and you might think of what is in Palo Duro Canyon relative to what we see here in western Tennessee and western Kentucky and up into Missouri, Illinois. Palo Duro Canyon is kind of the inside story to the structure and process that's formed the Great Plain. What do you see? You see the red beds, or the red muds, very prominently in the area, and they're slightly inclined. And then up above that, you see this layer of gravel, Ogallala conglomerate. Okay, and that's usually 50 to 100 feet thick over the plateau, over the surface of the Great Plains. And that formation, the Ogallala conglomerate, because it's porous, makes for the wells and the water being at the surface. The finer grained sediment underneath is not a strong aquifer, so the aquifer is at the surface, and of course you have lots of wind-blown dust or loess. And so that's the fertility of the Great Plain right there, and seeing that the layer and the wind-blown dust deposit. Again, another look at Paladuro, this time a little bit elevated. You see the surface of the Great Plain right there? Okay, it's a conglomerate or gravel deposit sitting on the flood rocks underneath. So the flood, post-flood boundary is right there. Okay, I can see it, I can imagine it. And of course, what do you see? The planar erosion surface, okay, beveled surface, and then channelized erosion. And then I can pick the flood, post-flood boundary, what I think is right there. That gravel deposit has all kinds of mammal fossils in it, and it's evidence of mud flows, essentially. The large part of the Ogallala conglomerate is high concentration slurry flows, mud flows. And that shows us what it was like in the post-flood period. You had mass wasting. And there are boulders in Ogallala and Cypress Hills, gravels up north in Montana, Wyoming, that come fragments, football-sized fragments of quartzite that have moved several hundred miles, a couple hundred miles from the Rocky Mountain front. So those gravels and the pebbles in there show you local sources, but rather widespread blanket of conglomerate. So it gives us a perspective on the flood and the post-flood boundary. Again, the top of the Great Plains, looking at Paladuro Canyon, there's the Ogallala conglomerate. There's the red beds, the mud, flood deposited mudstones underneath it, the red strata. And so that's the whole picture of what the Great Plains is like. Okay, you go up into Wyoming and into Utah, Colorado, Wyoming, Utah, Colorado, and you see this at the surface. You see what's called the Green River Formation overlaying the Wasatch Formation. The Wasatch is the formation you see like at Bryce Canyon, and the Green River Formation is very obvious up in southern Wyoming and southern Wyoming in the Green River Basin. And so the Green River Formation overlaying the Wasatch. And what about the Green River Formation? It's localized into basins. Do you see the way it's drawn? The shaly and limey rock is thought to be a deposit in a basin, in a lake, or a couple of basins that have been overtopped. Uinta Basin and down into Colorado into Utah. And then there's Green River up above. These basins are very much evident in the way the deposit changes as you go horizontally toward the edge. And so the thing that's called oil shale in the Green River Basin is really what? It's a limestone sediment. It's a calcium carbonate precipitate, very fine grain, and it provides evidence of a lake. So there was a lake, okay, a post-flood lake sitting there, and that's a fossil lake. And we'll talk more about the organisms in the lake in a minute, but that's the story. Okay, wedge-shaped deposits, right? We have deposits confined to basins, one of the characteristics of the post-flood. So you can argue that Green River Formation is a lake, post-flood lake deposit. It's called Eocene, so under Eocene is this boundary, post-flood boundary. And then let's talk about deltas. Nile River Delta, okay, what do you have? A wedge-shaped deposit associated with an uplifted continental mass, and then, of course, the ocean floor, Mediterranean Sea. Continental sprint produced the upwarp of the continents, and the ocean basins closed up the Mediterranean. And then, pardon me. Okay, the geophysical surveys show that deltas, river deltas, are extremely broad things. The Mississippi River Delta is a gigantic wedge of sediment. It's in places, it may be 6 miles deep. Okay, offshore Louisiana, they've drilled 6 miles. Okay, and they're in, there's gas in those rocks. And so oil companies are very interested in this. And the geophysical surveys illustrate the depth of those wedges. So you see you see the delta at the surface, and then you need to think about what's down there, and that's a wedge. The wedges need to be detected by some characteristic, but when you appreciate that the wedge of sediment is sitting there, such as drilling or geophysical survey, that is an argument, I think, for post-flood. So where did all of the sediment go that was eroded off the Colorado Plateau? Where did the sediment go? And those strata, there's thousands of feet of erosion off the Colorado Plateau, especially in the beveling in the late flood and the post-flood. So that late flood and post-flood sediment is going to be largely in wedges sitting in low areas and at the boundary between continental shelf and ocean floor. Okay, now we need to think about sediment from local sources. For example, alluvial fan is a no-brainer, right? You've got what? You got a sedimentary deposit sitting there at the Piedmont front of a mountain, and you have up there the source of the grains, and they come down and form an alluvial fan. Okay, in the deserts you have what? Mountains. Okay, mountains. You have alluvial fans. You have coalescing alluvial fans called bajadas, coalescing alluvial fans, and then you have playas. Those are dried up lakes. Okay. And then you have pediments. Those are surfaces of erosion flanking an elevated mountain and at the boundary between the elevated mountain and the down-faulted basins, okay, and vertical tectonics taking off there. Pediments or erosion surfaces can form. And then we have sand dunes and other things, and badlands. All those are what? Those are post-flood topographic features or landforms that form the landscape that's been made in the post-flood period. Anza Borrego Desert State Park in Southern California. Where did all the sediment go that was excavated from the Grand Canyon? The Grand Canyon flood surface is a plateau that's been beveled, okay, and then in a post-flood, channelized erosion making Grand Canyon. Grand Canyon is about 900 cubic miles of sediment to fill it in. So we excavated in the post-flood period 900 cubic miles of sediment. Where did that go? It went down into Anza Borrego Desert in southern Salton Trough area in Southern California. And here we are. We're looking at the deposit that was once in the Grand Canyon, the sediment that was in the Grand Canyon. And it's a kind of a shallow ocean and lake, okay, in the post-flood period. And it's a badlands, okay, that's Borrego Badlands. And so badlands is a landscape that's formed. Gully and rill erosion on a widespread area in the drier climate that we've experienced, and so the drying of the earth has created these badlands areas. And then ultimately deserts. Okay, deserts are what? Post-flood features. And landforms in deserts like dunes, all that you can see and appreciate post-flood. Okay, let's talk about volcanoes. Volcanoes scale down, and we see some of the argument for that. The brushy basin member of the Morrison Formation, shown in red, and it's a huge deposit. It's buried underneath all the other volcanic deposits in the western United States. That brushy basin member likely was fed from fissures, linear fissure array in California up and into Baja California down there, and the enormous supervolcanoes shed this volcanic debris, probably in the late flood. So I think of that as a late flood, and then on top of it comes all of these post-flood volcanoes. Do you see what happens there? Yellowstone eruption is huge, 2,000 times Mount St. Helens size. Then Long Valley caldera in central eastern California. The Bishop Tuff is a welded tuff with fused pumice fragments embedded in a matrix of fused volcanic ash, 150 cubic miles of ash in the Long Valley kind of thing. And then, of course, we have Crater Lake eruption in the post-flood period. Mount Mazama there in southern Oregon, that erupted and then collapsed to make Crater Lake. 17 cubic miles of ash spread around obviously in the post-flood period. And then Mount St. Helens, trivial, a quarter cubic mile of ash. Okay, volcanoes scale down after the flood. And these large-scale volcanoes that are in the post-flood period that are buried provide the evidence that we need to look at for exposure. And so volcanic evidence of exposure. Here you see the Columbia River basalts, okay, in eastern Oregon, northeastern Oregon, and you see underneath the John Day Formation and the Clarno Formation. The Clarno, John Day, and the Columbia River basalts form that sequence. And we look at the John Day Formation, and what do we see? Welded tuffs, thin layers, just tens of feet thick, with fused pumice fragments embedded in a matrix. It fell on a dry surface. And the lavas that form the Columbia River basalt, some of those lava flows cover 10,000 square kilometer area and hundreds of feet depth. It was a lake of lava. And many of those lava flows in there show no evidence of pillow basalt. There are some of the Columbia River basalts that flowed into depressions, probably with water in them, maybe lakes, but not generally. That's not the characteristic of the Columbia River basalt. It was an exposed surface. So evidence of emergence and indicating post-flood features. And of course, we got the welded tuffs and the other things that argue for. And there may be even Paleosol evidence in the Clarno Formation. Some of these weathered volcanic ash quickly weathers, and it was buried. So those are tip-offs that we're looking at flood sediment. Then underneath this sequence, we have what are called the Cretaceous Strata, and they show evidence of the ocean over Oregon. And generally in the Rocky Mountain area, the last evidence of the ocean over that area is in Cretaceous, so-called Cretaceous Strata. So this is post-flood. This is a post-flood sequence here. Here's the Green River Formation. The Green River Formation contains a complete lake ecosystem. You see the exclamation point on there? I want to affirm that so other creationists can come to the appreciation that I have. The Green River Formation is known for its herring fossil fish, right? There's those fossil fish. There are big fish, lots of big fish in there, but that's the general characteristic. It looks like freshwater fish, okay? And the freshwater fish are associated with terrestrial plants like the frond of palm and other freshwater plants or terrestrial plants, and then turtles. Do you see that? Here's a bat fossil, and here's a wading shorebird fossil. Okay, so everything lends itself very nicely to a lake interpretation of the Green River Formation. It was a post-flood lake. It sits on the Wasatch Formation, which also merges with a gravel layer called the Ogallala Conglomerate in Palo Duro Canyon in Texas. And so that whole wedge of sediment is surface sediment is associated with what we see in the basinal deposit in the Green River Formation. Okay, and then animal and plant distribution after the flood. You might think about this. Today we have what's a mammal dominated assemblage, okay, different than the pre-flood. And then, so what happened? Oh, this was, it radiated from over here, not over there. So anyway, that's animals and man repopulate the earth from Mount Ararat and Tower of Babel. And so we want to think about the post-flood distribution of animals. Does it take millions of years or hundreds of years to reestablish an ecosystem once it's decimated? Mount St. Helens shows just in a couple years after the eruption that animals and plants were back on the surface. And today we have 37 years after the eruption of Mount St. Helens, we have a habitat largely recovered from the 1980 event. And animals have all these unusual behaviors that allow them to flourish in the difficult situation, like at the blast zone at Mount St. Helens. Elk have this ability to eat grass, right? And we think they like the grassy slopes in the blast zone at Mount St. Helens more than they like the forest. We thought elk were a forest-dwelling animal. They can do very nicely in that. And we thought that elk were going to overheat because they can't find shade in the blast zone. Boy, the biologists were wrong. They have a cooling behavior, and they're doing very nicely out there. And then the whole habitat's recovered because pocket gopher have churned up seeds to the surface, and animals and plants bring in seeds, and the conifers are growing, and lots of nutrients because lupin and other nitrogen fixing plants quickly restored the soil and made it very productive. And then, of course, the last thing to happen in the post-flood period is ice age, and you want to look for ice age deposits. When you see evidence of glacial deposits, that's the after effect of the flood, and obviously in the post-flood. And there's Yosemite, Big Valley Glacier occupied this, and so glacial deposits are obviously post-flood. Okay, I'm basically done here. Here's my list of criteria, my 7 criteria. I've talked about horizontal tectonics giving way to vertical tectonics, and I can see vertical tectonics in Eocene, Green River Basin. I can see vertical tectonics in the Colorado Plateau, the upwarp of the uplift of the whole Colorado Plateau that formed in the late flood and in the post-flood. And then I can see beveled erosion surfaces. The character of erosion has changed from the flood erosion, general widespread erosion, to channelized. Sedimentary deposits confined within basins. Okay, those basin confined are tip-offs of post-flood. And then wedge-shaped deposits adjacent to elevated surfaces, big deltas, and sediment derived from local sources, such as some of the features I've seen in the Anza Borrego Desert in Southern California. Sediment derived from local sources, like not that local, but the Ogallala Conglomerate, a post-flood layer of sediment in the on the Great Plains. That's associated with fragments from of rock from the Rocky Mountain area, and although it's not that local, it's is a tip-off of post-flood situation. Post-flood mud flow surface in the Great Plains. Evidence of emergence, especially in volcanic deposits, especially scoriaceous upper surfaces of lava flows without pillow basalts, and welded tuff beds. Those argue for emergence. And so volcanic deposits especially signal emergence, and so you can see that in the post-flood. And then complete fossil ecosystems appear with modern flora and fauna. That is also a diagnostic criteria of post-flood process. I'm done. Questions?
Is there a general flow of sediments from like east to west, or are they all level over the face to the land or shifting?
There's a general direction that we see for flood sediments. We see dominant directions for flood sediments, but we don't see dominant directions in post-flood because they tend to be basinal. Although the Great Plains obviously flow from the elevated areas to the west and the east, right? We have the Appalachian front that was uplifted in the late flood, okay, and so this is kind of a large basinal area, and the Great Plains is the in between the big uplifts. That's a good way to look at it. Other questions? Yes.
So you're saying the continents separated after the flood. How would you explain?
They separated during the flood.
Yeah, during the flood. How would you explain the animal distribution over continents?
Okay. Well, they distributed widely with the continents in the present area. Kurt will discuss about that. But I'm dealing with boundary criteria, and that's a controversial subject among evolutionists, and or among creationists. The boundary criteria for the flood post-flood boundary. Some people put the flood post-flood boundary directly under the Ice Age deposits, not under Green River and other deposits sit underneath there. They don't imagine lakes in northeastern Arizona, no lake basin there. Okay, simply the retreat of the flood also beveled the surface and also channelized the surface. Okay, that's an alternate way of thinking. I dispute that. Okay, and so that's my my special take, and I think I'm speaking generally for the creation geology community when I say that the flood post-flood boundary is somehow buried rather deeply underneath the glacial deposits, not right underneath the glacial deposits. Okay, other questions?